So for an elementary particle with wave function psi, the equation satisfied by that function is called the Schrodinger equation, and it's given by this right here. So we've got I, that's the imaginary I, h bar, that's the renormalized Planck's constant, psi sub t time derivative is equal to h bar squared over 2m, where m is the mass. And then we've got the second space derivative of psi plus the potential energy times psi itself. Okay, so we're not going to worry about the derivation of this using potential energy and momentum. We'll just talk a little bit about the solution. So one thing that's worth noting is that if the potential vanishes, then we get what's called the free, as opposed to forced, Schrodinger equation. And so the free Schrodinger equation looks like psi sub t is I times psi sub double x. And so this one looks a lot like the heat equation or diffusion equation, but due to the fact that there's this imaginary I here, it actually turns out to be qualitatively different. However, we can still go about looking for solutions in more or less the same way. So we're going to look at an idea called separation of variables. And we'll talk a lot about separation of variables later on. It turns out to be a very powerful and common solution technique. And so the idea is to look for solutions which are a function of space alone times a function of time alone. And so the idea is that there's no t's appearing anywhere on the left-hand side, and there's no x's appearing anywhere on the right-hand side. And so are you guaranteed to have a solution of this form? Well, no. But if you happen to find one that does have that form, then you've got a solution and you win, right? So give it a shot. So let's see. So now what we do is we say, okay, so suppose there's a solution of this form. Then if we substitute this into the equation, time derivatives will only affect phi, and space derivatives will only affect y. So let's substitute this guy in to Schrodinger's equation and see what happens. So let's see. So on the left-hand side, we have I, h bar, and then we have the time derivative of psi. So that's going to affect the time part, but not the y part. So I have y phi prime. Meanwhile, on the right-hand side, I have minus h bar squared over 2m times the second space derivative. But if I do d dx to phi, it goes right on through. It treats phi like a constant. So I have y double prime phi plus, and then I've got the potential. So v, and then we've got y phi. Okay, and so here's where the magic comes in, is if I divide this equation now by phi and y, then on the left I have phi prime over phi, and on the right I have minus h bar squared over 2m, and then I'm going to have y double prime over y, and here I'm just going to have v. Okay, so let's see what happens now. Well, now at this point, there is no t anywhere on the right-hand side. There's also no x anywhere on the left-hand side. So for instance, the left-hand side, since there's no x's anywhere in it, if I were to apply the partial differential operator ddx to the left side, I would end up with 0. Okay, so then that tells me that on the right-hand side, this has to be a constant function. And that reasoning is totally symmetric. So doing it the other way around, let's see here, tidy this up again, boom. If I were now to apply, let's see, so there's no t on the right-hand side, so if I do ddt, I would get 0 over here. So the only way that that can happen is again, if it's a constant. So it must be the case then that that this corresponding expression here, both sides of it, need to be equal to some constant. And so we'll call that constant E. For energy. Okay, so now let's see. So now if I look at the fact that the left side is equal to E, we get well here. We get 2 ODEs out of this formulation. On the left side, we have phi prime over phi is equal to E divided by IH bar. So we get this one. And then from that one, I'm sure you could solve it very readily without any kind of strain. This is CE to the minus EI T over H bar, so some exponential. And then from the fact that that this part in the middle here is also equal to E, we get the other equation. And that one tells us that, let's see, we will have, tidying it up a little, y double prime plus v minus E over I H bar times y equal to 0. Okay, and so this one is called the time-independent Schrodinger equation. It turns out to be very fundamental for quantum mechanics, and a large part of the reason is the following. So if we look to Euler's formula from power series, e to a purely imaginary looks like cosine plus I sine, right? So in particular, that tells you that if you have a purely imaginary exponential, it has magnitude equal to 1. Because its magnitude looks like cosine theta plus cosine squared theta plus sine squared theta by the Pythagorean theorem. Okay, so that tells you that this phi that we found is an oscillatory function with magnitude equal to 1. Actually, here, let me remove that constant. Boom. Okay. Now, is definitely equal to 1. Okay. So if we look at the integral, and actually, oh, you know what? I want the arguments. Let me write the arguments. Xt squared dx. Okay. So then based on the fact that psi has the form of yx times phi y, then this is going to be magnitude squared of y times magnitude squared of phi. But then we just saw that this part here is equal to 1. So that gives us integral y squared dx. All right. And then it turns out that as a consequence, the values that we don't always have solutions. It depends sharply on the value of E that we have. So the values of E for which we have a non-trivial solution y. And now in order for it to be a solution, realize it has to satisfy not just this differential equation right here, but also the constraint from before that, where'd it go? Oh, that was on the previous slide. The constraint from before that the integral be equal to 1. So we need the integral of y squared to be equal to 1. So that we have that psi when squared has modulus equal to 1 and is a bona fide probability distribution. Okay. So these values are the allowable energy levels. So if E is not one of these values, if your energy value or your energy level is not one of these particular values, then you won't get a non-trivial solution. And so the crazy thing about this is that this gives you quantization. Because only certain distinct or discrete values are allowed, as opposed to in classical mechanics, where any energy level is possible.